Okay, good afternoon, everybody. It's a pleasure to welcome Max Josef FAHN from the University of Bologna. He finished his PhD in 2024 and started at 2021 with Christina Giesel, working on various gravitationally induced decoherence, which is also the topic of today. And then in 24, he moved to University of Bologna as a research fellow. So thank you very much.
Thank you very much.
Is there an echo?
Yeah. Is it coming from the speaker here, maybe?
Yeah, nice. Because we turned on the speakers.
Okay. Hello, everybody, and welcome to this talk. I'm happy that so many of you showed up today. And of course, thanks a lot for the opportunity to speak here today and to present my research. So I'm Max Josef FAHN, currently postdoc at the University of Bologna. And thank you very much for this kind introduction. And today I will talk about gravitational-induced decoherence. And as a little warm-up, let's maybe quickly talk about quantum mechanics. And when we deal with quantum mechanics, what we often do is that we treat isolated quantum systems whose dynamics we want to work out, and the dynamics of this isolated quantum system is then given in terms of the Liouville-von-Neumann equation for where the state of the system is encoded in this density matrix rho s here, and the Hamiltonian of the system is Hs, which induces this dynamics. And we only get unitary dynamics from this. However, when we move one step further and consider open quantum systems, that is, we consider a quantum system of interest, but which is somehow subject to some external influence, and we also want to encode this influence and information of what is going on around and how this surroundings, this environment influences our quantum system, then we can write down a modified version for the time evolution equation, which is called the so-called master equation. And you can see, in addition to the standard terms from the Liouville-von-Neumann equation, we get additional red operators, red terms here. One contributing to the unitary evolution, and another term, a so-called dissipator term, which can lead to also non-unitary effects. And some effects which are encoded in these red terms and come due to the presence of some environment are, for instance, energy shifts or renormalizations in the system of interest energy levels, dissipation, which is the flow of energy from our system of interest into the environment, or also decoherence, which roughly speaking denotes the vanishing of the off-diagonal elements in some specific basis of the density matrix rho s, describing the system of interest. And then this leads to a loss of these interference probabilities and to some kind of, if you want to call it like this, classicalization of our system of interest. And I'm in particular interested in this open quantum systems formulation because thinking of some applications to systems where we cannot track all the detailed dynamics of our environment because it's too big, because we can, for instance, not measure all the details which are going on there. And then this open quantum system formulation provides a helpful tool to effectively implement the dynamics of this environment. And for me, what I want to talk today in this talk about is in particular an environment somehow being gravity. So mostly it will be linearized gravity, later also a bit moving towards black holes and horizons. And the main questions that arise in this open quantum system formulations are then how actually these red terms in this master equation look like and how they can be derived if the environment is gravity. And in a second step, as some kind of application, also how do signatures of such a decoherence effect look like in some specific physical settings. So in today's talk, we will derive and solve some master equations for matter in an environment of gravity. And the overview of the talk is the following. It consists of 4 different parts. In the first part, we will consider a field theoretical model of some bosonic matter field coupled to an environment of linearized gravity and then derive the master equation for this bosonic matter field. In the second part, we will project this onto the one-particle sector, meaning that we are only interested in the dynamics of one single bosonic, or in the particular application, one single scalar particle moving through this environment of gravitational waves. And then we will use this to make a toy application to neutrino oscillations and gravitationally induced decoherence on them. And in the last part, we will talk about decoherence induced by horizons, in particular black hole horizons with classical and quantum geometry. And What I mean by that is I will clarify later in the course of the talk. Okay, let's start with the first part, a field theoretical master equation with linearized gravity as environment. And this is work which was conducted in collaboration with Christina Giesel, Roman Kemper, and Michael Kobler at the FAU Erlangen-Nürnberg. And the setting we are interested in is that we have some bosonic matter field which is coupled to GR. And then we consider a linearized version. This means we linearize our metric of GR around a flat Minkowski spacetime plus some metric perturbation. The linearization parameter is kappa, the kappa from the Einstein equations. And then our system actually looks like this, that we have some fixed flat Minkowski background. And on this background, we have two fields, namely the linearized gravitational field, which corresponds to gravitational waves, and our bosonic matter field, which we are actually interested in. And then, to start with, one can write down the classical action given by general relativity, coupled to the matter field, linearized GR, obtaining this linearized metric. And this here is already written down in the Hamiltonian formulation. This is the ADM 3+1 split by introducing the spatial metric plus its canonically conjugated momentum from the original form metric. And then the matter coupled to GR. And the good point when starting from this, or one favorable point, is that we do not have to impose how the coupling looks like by hand, but GR tells us how the coupling looks like. This is something which is an advantage from the field theoretical models. We will see later in the quantum mechanic models that there it's more complicated to come up with an appropriate coupling term. Okay, and starting from the setting, there are several works in the literature that follow then paths to a master equation, and I quickly want to outline what is there. So the starting point in the works I'm considering here is always the same, an action of linearized gravity coupled to a bosonic matter field. And then the first class of works considers as the dynamical variable for gravity the metric and its canonically conjugated momentum, and then go into either specific gauge fixings for the gauge degrees of freedom which are there in the geometric sector and also probably in the bosonic sector, depending on which kind of field you choose. For a scalar field not, but for a photon field, for instance, you have some gauge freedom. And another class of works do specific gauge fixings for gravity and constructs Dirac observables for matter. And in our work, we try to do a slightly different route, starting from a reformulation of linearized gravity in terms of the so-called Ashticker variables or Ashticker-Barbero variables, which phrase gravity into a theory similar to Young-Mills gauge theory. You might recognize this here. It looks a bit like electrodynamics, very roughly speaking, but with an additional index. And this additional index here is an SU2 index and has the advantage that you can also couple in some later step directly fermions to this. Whereas for gravity, you would have to rephrase things into field binds and triads. Here you can couple it directly in this internal index. But the cost of reformulating it like this is that you get some additional constraint, a so-called Gauss constraint. And we used these variables as one motivation was the coupling of fermion in some later project, which is easier possible here. And another motivation is that these are the basic classical variables used for loop quantum gravity. So one can also change the quantization procedure. It's also in the future at some point. So we used here a Fock quantization still. And then we formulated the dynamics in terms of relational observables. That is, we picked classical reference frames. And these are the two works. In particular, the first one from 22, dealing with a scalar field as a bosonic matter component. And the second one, hopefully from 25, dealing with a photon field as matter content. Now let's dive into this and start at the classical point. Given this action, let's consider how to deal with the gauge degrees of freedoms. As I said, we decided to use classical reference frames following this relational formalism introduced in a series of papers here. And in principle, this relational formalism is a method to deal with gauge degrees and gauge freedom in physical systems and to formulate dynamics. And while a gauge fixing is some specific choice of gauge, these observables and this relational formalism allows to compare different gauges. And the basic idea is to describe evolution and dynamics of some part of the system with respect to another part of the system. So with respect to other degrees of freedom in our system. And the space and time coordinates in GR, which there are at some point just gauge degrees, gauge coordinates, can then be replaced with length and time dictated or defined with respect to this reference fields and to these observables. let's go a bit into detail. So the main idea is to use this so-called observable map to construct these Dirac observables for the theory. And this observable map here takes some gauge variant quantity f, and then some set of clocks or reference fields or rods, whatever you want to call them, and some parameters which you can read off from these reference fields from these clocks. And then you plug this into this exponential map here, where psi I is here ti minus tau I, and ci denote the constraints which are present in the system. And this here is the Poisson bracket. And then this map spits you out some Dirac observable. This is some quantity which commutes with all the constraints by construction here. And the idea is, the physical idea, I would say, is that you ask, okay, what does my system look like if my reference fields, my clocks show value tau I? And then this observable spits you out what the gauge invariant version of f looks like if you put in these parameters in the system. And what you have to do there, if you want to apply this formalism, is to construct suitable clocks T. And there are different methods. So one can either, for instance, use some meta degrees of freedom, introduce dust fields into the system, and construct clocks with respect to these meta degrees of freedoms. And we decided here to use geometrical clocks. That means we considered the degrees of freedom from the geometry and built our clocks out of them. And these clocks, what we wanted them to fulfill was that they are canonically conjugated to exactly one constraint, that they commute among each other, and that they also commute with these Dirac observables. There's a pretty long list of requirements, but we will see in a moment why we impose them like this. And after some work, you can find clocks. Of course, they're not unique. You can build different clocks, whatever you like. And we followed these clocks here, somehow a bit inspired by gauge fixings. For instance, this one here, this clock is meant to be the clock for, so it's always canonically conjugated to one constraint. So the clock for this new Gauss constraint, one obtains this Ashtiger formulation. You can see this somehow resembles a Lorentz-like gauge fixing, where delta A is some geometrical degree of freedom. The star denotes a convolution, and G delta is the inverse of the Laplace operator. So something like the Fourier transform of 1 over k squared. And then here, delta t is the clock related to the Hamiltonian constraint, so which induces time evolution in this ADM split. And therefore, the associated parameter tau, this clock parameter tau, would be what we call the physical time coordinate then in this relational formalism and in this classical reference frame here. And you can see it also consists of delta E and delta A, so purely of geometrical quantities. And delta TA is the spatial clock, which is conjugated to the spatial diffeomorphism constraint. And there it's a bit longer and more complicated, so I didn't write it down. But here the associated parameters would be what are the physical lengths in our system then. Then given these clocks, we can use the observable map onto the remaining quantities, which would be phi and pi, so the scalar field and its canonically conjugated momentum. And for geometry, we have delta E and delta A. And it turns out that only 2 degrees of freedom here are left after these maps. And these so in each of them, there are 2 degrees of freedom. And if you want to rephrase it in terms of the standard linearized metric, then you will find that they precisely correspond to the x and the plus polarization of gravitational waves. And just to give you a glimpse on what these observables look like, so this would be the observable we get for the scalar field phi, given this set of clocks here. So I omit this t down here always because I always refer to this set of clocks here. And then you get a first ingredient, the standard scalar field. And then you get some higher order terms, so higher order in kappa, which compensate for the gauge transformations in phi. So if you do some gauge transformation of phi with some constraint, make the Poisson bracket, then these additional terms here, consisting of the clocks and also a bit the meta degrees of freedom here, would precisely compensate for these gauge transformations. So the entire observable is indeed gauge invariant. Okay, so yes. Here, yes. So delta A is a geometrical degree of freedom, and the star is a convolution. And then G delta is the inverse of the Laplace operator, so the Fourier transform of 1 over k squared, if you want. And then you can calculate it. So we actually calculated this in the Fourier space, and there it looks a bit nicer, but to see what actually happens, the position space in the end is a bit more helpful, I would say. So that's why it's written in this rather complicated form with this. Yes. This one? Yes. So this would be the clock or the reference field which fixes the gauge freedom, or which is canonically conjugated to the additional Gauss constraint we obtain. And for me, it's also not really straightforward. So this Gauss constraint, what it does is it creates some kind of rotations in this internal space I here. But as this was introduced somehow, in addition, this is not present in the standard metric formulation, I'm not completely sure if there is a one-to-one physical correspondence. That's why also we set here the parameters related to this clock to 0 everywhere, and the one which are the physical ones are in particular these two here, which give the time and the length coordinates. So. Which shift? Yes. They are also here, so it's a bit complicated to see. If you want, I can show you afterwards in the formulas. Maybe it's easier. But they're also then in here, more or less, in this, because the lapse and the shift. Yes, the lapse and the shift would be the quantities that determine this. This shift or this translation on the spatial hypersurface and orthogonal to it. And this is then what these clocks more or less deal with or fix, if you want, like this. Okay. Now, given these observables and the set of observables, why do we put so many requirements to these observables? That all of the specific commuting things we had, the clock should commute with each other and so on. The reason is that now, what we can do is a canonical transformation of our phase space variables from phi pi and this delta A, delta E, so the original degrees of freedom in our phase space, to this new set of degrees of freedom, which consists of the clocks and the canonically conjugated constraints, as well as the observables. And by constructions and the requirement we had to these observables, all of them commute now with the clocks and the constraints. So they form a closed subalgebra, which allows us to make a reduced phase-space quantization and only quantize these degrees of freedoms, which indeed are the physical degrees of freedoms. So the polarizations of the gravitational waves and the scalar field and its momentum. And then one can perform such a Fock quantization, ends up with a Hilbert space, which is a tensor product of the Hilbert space of the system, so of our scalar field, or the observables corresponding to it, and the environment, which would be these gravitational degrees of freedoms. And we can make a standard mode expansions as usual in the Fock quantization, and associate A and A dagger as annihilation and creation operators to our scalar field, and B and B dagger for the gravitational field, for the gravitons, if you like to call it like this. And then the only thing in this mode expansion which looks a bit different here is that you get some polarization tensor, which projects onto the symmetric transverse traces degrees of freedom. It's a bit similar to how you quantize photons or electrodynamics. They would also get this polarization tensor. And then you can write down the total Hamiltonian from this classical action in this quantum field theory, and it can be split into a part which gives us the evolution of our scalar field, part that gives us the evolution of the gravitational environment, and an interaction part, which tells us how these two interact with each other. And with this, we have set the stage for our quantum theory, or quantum field theory, and we can continue to derive a master equation to obtain the dynamics of our scalar field without having to care about the details that are going on in the environment, but still with its influence on the scalar field. So what we want to do is, starting from this Liouville-von-Neumann equation for the entire system, or for the total system, rho t, which is closed as such, and we want to go to this open systems formulation for only the dynamic equation for rho s, so for our scalar field, with this influence of the gravitational environment encoded in these red operators here. And to do so, there exist several different ways. Two of them are, for instance, a projection operator technique or a Feynman-Vernon influence functional approach. And in this first part, I will explain the projection operator technique, which we used there, and later we will see some application of the influence function approach. But of course, there are different ways and or more methods, and for this specific example we are considering here, indeed both give equivalent results and look equivalent in the specific approximation. So the projection operator technique consists in introducing two projectors P and Q, or also super operators because they act on density matrices, and the projector P is called the projector onto the relevant part of the Hilbert space, because what it does is actually traces out the environment, so degrees of freedoms we are not interested in detail, and then appends, just for dimensional purposes, some environmental reference state, rho e. And Q is just 1 minus P and the projector onto the irrelevant part of the Hilbert space. And then the idea is to apply both projectors to this Liouville von Neumann equation, solve the one for Q approximately, and then plug it into the solution into the differential equation for P to obtain a closed differential equation only depending on P rho, so only on rho S. And some approximations which are often invoked there is to first assume that the environment, this gravitational waves environment or this graviton environment, is given by a thermal state, rho e, with some temperature parameter T. And then one often truncates this master equation after the second order in square root of kappa. And what one ends up with is then this form of the master equation. So indeed, as we saw in the beginning, this has the desired form of this master equation. We have the evolution of our scalar field, and then the influence of this gravitational environment in some gravitational self-interaction term, some lamp shift-like term, and a dissipator. And for this field theoretical setup, this master equation looks pretty complicated, so that's why I didn't write down the details. But this brings me to the next part of the talk. Namely, it would be good to apply further approximations on this equation in order to make it somehow solvable or get some more idea of what is going on there. And to connect to physics and experiments, it's also a good thing to have the projection onto the one particle space. So to be able to read off the influence and in particular the coherence of one single scalar particle. This brings me to part 2. This is a work which was done in collaboration with Christina Giesel, namely the one particle projection of the master equation. And what we want to do now is, starting from this setup which we ended up with in the first part of the talk, going towards this physical picture, to have one single scalar particle propagating in this environment of gravitational waves. And the first step of this one particle projection consists in substituting the density matrix here with the density matrix of one single particle. Here it would be a momentum representation, so we have momentum values P and Q, and then here we have the density matrix in this momentum representation, and indeed just one particle here, so A dagger P and AQ, which gives us only a one particle state. And then this projection is usually made pretty, I would call it drastic in the literature, but to get this first glimpse, and then namely all the terms which would project out of the one particle space are dropped from the right-hand side of the master equation. Yes? Because in the density matrix, it's a bit like you would have the direct product of one cat and one bra. So it would have two states, or I don't know how to phrase it well, but in this density matrix, this corresponds somehow, if you want, if it's a pure one, to cat psi times bra psi. And then this formulation here is helpful because we will see later some results in some very simple example, and then it becomes obvious that one cannot simply write down a state anymore, but one needs really this density matrix formalism. Or it would work otherwise also, it would be a bit more complicated than the states, but...
Yeah, I was wondering, because in finite quantities, you can write down an arbitrary density matrix as a sum of pure states, or a quantized sum of pure states.
Yes.
So this cannot be an integral only over 1p.
Yes, so this is, I would say, maybe the general form or something, if you like. So if you have some, if you write down this like here, with some wave function psi of pi, p, and then you have here your, I don't know how to, your state, like this, for instance, And then for the density matrix, you would take it, as you say, as something like this. And then you just need two different momentum labels there for these integrations, because a priori they're not equal. This would mean this density matrix is diagonal, which is fine in some bases, but in general not necessarily. So that's why one can write it like this. Think in the general form then. You like? Yes.
These H, L, and D on the left-hand side, are they exactly the same operators?
As on the right-hand side? No, not anymore, because we drop all the terms that project out of a single particle space. So one can split this. Oh yeah, sorry. Oh, thank you. Sorry.
I can imagine that from one particle sector higher.
Yeah. So actually I had twiddles there at some point, but unfortunately I think I dropped them. Thank you. But yeah, you would have in there, in this kind of, as it's based on this effective quantum field theory, you would have creation, annihilation operators, and usually 4 of them. So you would be able to create 4 particles or annihilate 4. And here we only keep the combinations that exactly always create and annihilate 1. And there may be again, but so that we always end up in the 1 particle space. Thank you for pointing this out. Okay, and such a 1 particle projection has been considered in some works in the literature, and the main challenges which arise are that, first of all, some terms on the right-hand side here are divergent, of course, due to working with this effective underlying quantum field theory formulation. So one has to apply a proper renormalisation, and the differential equation still is pretty complicated. So additional approximations are helpful to cast it into an easily analytically solvable form. And in the literature, the status was a priori that usually, first of all, approximations were applied on this 1 particle master equation. Then specific limits were considered. And in the end, some works performed a quantum mechanical renormalization by adding or subtracting suitable counter terms in the end to remove the divergences, or no renormalization was performed at all. And for us, we had the question if there is some way to understand maybe the origin of these divergences, connecting it to this underlying effective quantum field theory, and then also to be able to see the physical effects of the approximations, meaning that if we perform the approximations before the renormalization, some terms that drop out due to the approximations, it's not necessarily clear if these are physical processes or if they would vanish after renormalization. So that's why in this work here, we shifted a bit the order and started with a quantum field theoretical renormalization, and afterwards performed these approximations and went into specific limits. And the idea of this renormalization was the following, that in this work here, they showed that for a scalar field coupled to an environment of a scalar field, the individual terms in the master equation can be connected to Feynman diagrams. And then we used this and extended it to be capable for an environment of linearized gravity. Then one would obtain the following set of Feynman rules. This one here, the propagator for a scalar field of momentum k and mass m. The propagator for the graviton field. You can see it's massless, so there is no mass. You get some additional projector here onto the symmetric transverse traceless degrees of freedom. And this term here arises due to assuming the thermal state for this gravitational environment. So this is not the vacuum propagator anymore, but a thermal propagator. And n is the Bose-Einstein distribution, which has this temperature parameter T inside. And if you set it to 0, you would end up with a vacuum again. And then the interaction Hamiltonian expressed in this relational observables yields the vertices, and you get one vertex that combines one graviton with 2 scalar particles, where this T is the Fourier transform of the energy momentum tensor. And you also obtain some second vertex, which is of second order, and combines 2 scalar particles with 2 scalar particles, and has no particle in between to transfer this interaction. So somehow some known local interaction vertex. This was pretty interesting, but we will resolve it in a moment. It's actually due to this ADM split we made in the beginning, so working in the non-covariant form. But this, in a moment, more on that. And it turns out that in this connection that the UV divergences which arise in the master equation are from the vacuum self-energy of our scalar particle. So precisely from this Feynman diagram, it's fine with the 1 particle picture. You start with 1 scalar particle, end up with 1 scalar particle, but you have some loop in between, which causes the divergence. And in order to deal with this loop, we first restored covariance, and this can be done pretty similar to how it's done for quantum electrodynamics. When quantized in Coulomb gauge, there you would also obtain such a non-local interaction being the Coulomb potential, but once you restore covariance, you would get here a different version of this propagator, so you would get here space-time indices instead of the spatial ones, and also here some other formulation, and then this non-local interaction indeed drops out. So this is just a relict of working in this non-covariant formulation. And then this reformulation allowed us to renormalize the self-energy loop, and the effect of this renormalization was that it removed all the vacuum contributions from the dissipator term, so from this D in the end. And with this, we ended up with the renormalized one-particle equation and continued to approximations on it. And the idea was to simplify the master equation to make it analytically solvable, and physically desirable would be a completely positive equation. This is some equation which predicts only non-negative probabilities. They would say, sure, we want this, but the problem is that when deriving this master equation, truncating higher orders, we lose terms that would restore this complete positivity. So we somehow have to restore it by hand or be very careful on the domain on which we apply the master equation. And there are two approximations which do the job. The first one is the Markov approximation, where the idea is that the environment forgets rapidly about the correlations caused by the system, or in a bit more technical terms, that the timescales on which the environment and the system evolve are very different. The environment evolves on much shorter timescales than the system. And the second approximation is the so-called rotating wave approximation, where the idea is to perform some coarse graining of the time evolution, arguing that detectors cannot measure or resolve arbitrarily fast oscillations, so one averages them out. And then under these two approximations, one ends up with a pretty nice form of the master equation, nice in the sense of a simple form, the so-called Lindblad form, the Lindblad master equation, which is well studied in this realm of master equations. And this Lindblad means that this dissipator here has a very specific form, namely this one. It's some sum over some constant coefficients, so no time dependence here. And then there is some Lindblad operators Li and Lj. And then one sandwiches here the row, and then this is an anti-commutator. Yes.
You said, okay, we want to take this kind of QFT renormalization and then take further approximation. I forgot which one was this now. So, and restoring also the covariance. Then you end up with something which, in this one particle sector, is not complete positive.
Yes.
Okay, can you trace? So that was that this procedure was not good enough in a sense.
I would say this non-complete positivity arises from the truncation of the master equation. So I would say it's maybe a bit decoupled from this, that this is a renormalization, and we do this covariance there, so writing in terms of this 4 vectors and things, and renormalization there. But the dynamic equation which we have, we actually derived it before, cutting all higher orders in kappa, and then we plug in the solution, kind of the new Feynman rules. We get these normalized Feynman rules in there, in this master equation, but the form of the master equation remains the same, just the terms change, I would say. So this non-complete positivity came at this level of the master equation. Okay, and then we have here this Lindblad equation, and we can go into one dimension to see what is actually happening by assuming that this P and Q here of the density matrix are roughly parallel, and then one can write it like this Lindblad equation, and it turns out there's only one Lindblad operator, which is the system Hamiltonian itself. And this can then, due to this nice structure and due to only depending on Hs, solved immediately in energy eigenbasis of the system, assuming discrete energy levels, and one would obtain this form here of the solution for our one-particle master equation, where this is the standard unitary evolution what you would get, so this phase factor. And here we see an additional term which encodes the influence of this gravitational environment. It depends on kappa, so if we decouple these two parts of our system, say kappa equal to 0, it would vanish. And we can see that what it does is that on the off diagonals, so when EI is not equal to EJ, it causes some damping in these off diagonal elements, increasing with time and of course depending on the size of the prefactor. But this shows that in this specific model, in this application, this gravitational environment leads to decoherence in the energy eigenbasis of the system. And when waiting long enough, then these interference terms, these coherences on the off-diagonal elements in the density matrix would vanish at some point when waiting long enough. Yes?
So this is the energy of the one particle of the boson field.
Yes, yes.
So I guess if you're, I guess it's the momenta essentially. So it
Yeah.
disappears in plain waves.
Yeah. So,
But then if the scalar field rest,
mm,
which is relational observables, right? So it's not just the scalar
Ah,
field, it's the scalar field rest with the clocks.
yeah, expressed. So in this,
derived from the geometry.
yes. So we are all this T. I could have mentioned that this T is with respect to this relational observables, and also the X, which is not directly, but are this what I called tau before.
So the
It's just-
Newtonian just looks like the scalar Newtonian.
Uh,
The Newtonian of the system.
yes. But I think yes.
Quick question on the approximation basis.
Mhm.
So if you are relativistic
Mhm.
particle in there's Schrödinger term that T00 cannot be neutrally.
Sorry, there is.
There's a Schrödinger term which
Ah.
express energy
Mhm.
density. So like one might not be able to find energy basis.
Yeah, no, I agree. We just assumed it works out there and that this exists. We use this relativistic, or this ultra-relativistic case, or a relativistic Hamiltonian, where HS is more or less just a momentum. This is what we used here, but this is some toy application, I would say.
Like the eigenbasis of H.
Yes, of HS. So it's E is the eigenbasis of HS. But this is just some toy application in that sense, assuming that this exists and that this is discrete, and then we made use of it in the next part then. So just to give you some first impression maybe of how a result could look like of this rather technical formalism. Okay. Yes.
Where did you apply the rotating wave approximation?
Ah.
How is it?
How it enters? That's a good point. I tried to be quick on these approximations. In principle, the C here, I would say, in the first point would be time dependent and would also depend on continuous indices, on continuous variables like K and P or Q. And then the Markov approximation, roughly speaking, removes the time dependence of the C. And the rotating wave approximation in this case makes it easier diagonalizable and expressible in this nice Lindblad form. Otherwise, you would have additional terms here, and it would not look like this. So, very roughly speaking, this is the effect of these approximations here. Okay. You're welcome. Okay, then let's go on and use what we have learned so far to apply it and to come up with a toy model to neutrino oscillations and see how gravitationally induced decoherence might manifest there. And this was a project in collaboration with Alba Domi, Thomas Ewer, Lukas Hennig, and Uli Katz from the Erlangen Center of Astroparticle Physics, who are experimental neutrino physicists working on neutrino detectors and data, and with Christina Giesel, Roman Kemper, and Michael Kobler from the Institute of Quantum Gravity in Erlangen. And first of all, you might ask, well, why neutrinos? Sounds a bit random. The idea is that we use neutrinos because they are electrically neutral, so they are supposed not to interact too much, and in particular not to be distracted by electric fields when they propagate through the universe. And they have a very nice property, namely they have one basis, the so-called flavor basis. This is the basis in which they interact weakly and are created. And then there exist three basis states, electron, muon, or tau neutrino. And then they have a mass basis in which they propagate and interact gravitationally with three mass states. And the interesting thing now for this decoherence discussions here is that these two bases are not equivalent, but unitarily linked to each other with some unitary transformation U. So you cannot say an electron neutrino has mass m1, but you can only say if I measure the mass of an electron neutrino with certain probability I will get m1, with another probability m2, and with another one m3. And when the neutrino, which is created in flavor bases, propagates through the universe, this propagation happens in mass bases. And then if you measure the flavor of the neutrino at a later state, you might end up measuring a different flavor than the initial one. And if you do the calculations, write this down, then you see that indeed the probability to measure specific flavors oscillates with the time in which the neutrino propagates. And from this came up the question, okay, how does gravitation-induced decoherence look like there? Might it have an influence on these neutrino oscillations? And this has been studied in phenomenological models, often also closely linked to specific experiments and testing these decoherence models with neutrino experiments. And the typical procedure in these phenomenological Ansätze is to take a Lindblad equation and its formal solution, again in the energy eigenbasis, so what we just saw. But this time, this gamma ij, which encodes the decoherence, is not known microscopically. So one usually resolves it in this way, by some unknown but constant parameters small gamma ij, and by the mean energy of the neutrino, the mean kinetic energy, with some unknown power n. And then one tests this for different n's and for different values of gamma with experimental data and checks, okay, so far the experimental data does not show traces of gravitation-induced decoherence, so what is an upper bound for these phenomenological parameters? This is roughly speaking the idea. And this gravitation-induced decoherence then manifests in a damping of the neutrino oscillation, so in a change of the oscillation pattern. And for us in this collaboration, the question which arose was, okay, can we come up with some microscopic toy model, so in which we derive a master equation from some underlying Hamiltonian to find some possible resolution for these parameters. And for this, the model we used is based on this work here. And here they use a harmonic oscillator coupled to an environment of harmonic oscillators. And we then applied it to a neutrino Hamiltonian, one single neutrino, in this quantum mechanical model here, coupled to an environment of n harmonic oscillators to mimic the gravitational waves, with some specific coupling term motivated by the way how GR couples to matter. Namely, for GR would be the energy momentum tensor coupling to the configuration variable, the metric. Here we couple the system Hamiltonian to the position, which is all the configuration variable of our oscillators. And then one can perform pretty similar steps as we did in the field theoretical case to come up with a master equation. Assumptions would also be again a small coupling constant between neutrino and gravitational environment, and the environment, these oscillators being in a thermal state. Then in the next step, we took the continuum limit of the environment. So roughly speaking, sent n to infinity. So instead of considering single oscillators, we consider an oscillator continuum with some specific frequency distribution. And then we ended up with a Lindblad equation for neutrinos after Markov approximation. And this equation can be solved. It's very similar to what you have seen before. And in the energy eigenbasis of our neutrino provides us with this solution here. So indeed, it looks the same as the one we saw in part 2. We get the unitary evolution, and we get some damping term on the off-diagonal elements with some specific prefactor. And this is what we can use to compare it to the phenomenological models and find some resolution of this phenomenological parameters gamma and E, n, in this toy model. And it turns out that this gamma would be this thing here. So depending on the coupling, on the temperature parameter of the environment, and on the difference of the neutrino masses squared, which, by the way, is a property which is measurable. So we do not know the masses of the neutrinos, but we know the difference of the masses squared. And it turns out that the mean energy of the neutrino enters with a negative power of 2 in this toy model. And this is a result of how the coupling looks like of these terms in the original Hamiltonian. And yes? Yeah, this is a good question. So we assume in that sense, because it makes calculation analytically very nice, feasible. This projection operator formalism is also capable of using other states, which then would be more complicated. But I would say what our motivation was, we kept this thermal parameter open a priori. There are then works from cosmology, for instance, suggesting them value, I think, 0.9 Kelvin for primordial gravitational waves. And I would say, for me, it sounds like we have many gravitational waves with low energy, and the higher we go, the less gravitational waves we have. But if there is really a thermal distribution like this is something which I don't know, so which we assumed here really for seeing and using the techniques there. But of course, it would be very interesting to see how, if this can be matched and if there are better models for this. Okay, and having said this, there's one remark left in this toy model, namely that this match here of these parameters, which is done here nice in blue and purple, is only possible in the vacuum, because what the phenomenological models usually are interested in is a neutrino coming from the upper end of the atmosphere and propagating once through the Earth, where it's measured then in a detector on the other side of the Earth. And the presence of the Earth is usually included by adding an effective potential to the neutrino Hamiltonian, taking account for the weak interactions of the neutrino with the electrons in the matter of the Earth. And then here, as these terms here, these are the eigenvalues of the neutrino Hamiltonian. When we go into different layers of the matter, where the potential changes, also these values here change, and we get different values depending on the density of the matter for this eigenvalues for the Hamiltonian, whereas in the phenomenological models, usually gamma is assumed to be constant no matter what the effective potential is. So this is why this match here is only possible in vacuum. And if we go into matter, indeed the predictions made by these models would deviate. Here is an example of one neutrino coming from the upper end of the atmosphere, propagating through the Earth. And here we see black would be the curve for standard neutrino oscillations without decoherence. And red and blue include decoherence, gravitationally induced decoherence. The values here are chosen, in particular as coupling constants, such that one can see a difference and can qualitatively see what changes. Quantitatively, the coupling should be much smaller. So this is to make qualitatively the process understandable. And we see that the red line, which is our toy model, and the blue line, which is the phenomenological models, coincide while the neutrino goes through the vacuum, but once it enters the Earth, and in particular the core, where there's a lot of matter, indeed they deviate. So this match only in the vacuum also shows here in the plots. Okay, and with this, I want to come to the final part of the talk. Now we've always considered gravitation-induced decoherence in Minkowski spacetime. Now let's spice up this a little bit and go to gravitation-induced decoherence in some Schwarzschild spacetimes and coming from black holes. And for this, the base is actually a Gedanke experiment, which was made and published mainly here in Vienna. And the idea is that, and I will only take a very, very small amount of this experiment, which we used later then, so there's of course much more in this paper. The idea what we used then is that we have two experimenters, Alice and Bob, and Alice has some particle in a spatial superposition, which she keeps open for some time, and in the end recombines and checks if she has perfect coherence or not. She can do it, for instance, with a double-slit experiment. If there's perfect coherence, you would see the oscillation pattern you would expect. And then there is Bob, a second experimenter, who has a particle. And here we assume now that he releases his particle at some time. And then at some other time, t0, he might measure it or not. And these two particles are connected to each other by some either underlying electromagnetic field, if they're electrically charged, or by a linearized gravitational field. The reasoning goes rather similar, I would say, but I focus on the electromagnetic case. And then, if Bob performs a measurement at time t0, he obtains information about Alice's particle if the conditions are sufficiently nice. What this means is discussed more in detail here, but we assume that these conditions are fulfilled, so they are causally connected and so on. And then he obtains information on Alice's particle. If he does this measurement, this means that Alice's particle collapses. So her superposition collapses into one of these two position states. And then Alice, in the end, will realize this. And if Bob does not perform his measurement, her superposition remains open and coherent, and she will also realize it in the end, that she has perfect recombination. In this work here now, the main point was to discuss how causality and complementarity can both coexist, or if there are ways to, I'm sure many of you are familiar with this, or if there are ways to find some paradox are, but it turned out that both are maintained in all cases, which one can think of here. And in a succeeding work, the question was raised, what happens if Bob now sits behind a horizon? So inside a black hole, for instance, is it possible for him to send information to Alice via this process? Because it seems that his behavior behind the horizon influences Alice's superposition. And this was looked into starting in this work and in other works. And for this, let's go a bit more into detail and put into the game some specific protocol which Alice follows. The idea is that she starts with her superposition, with one particle, then opens the superposition during some time t1, keeps it open for a time interval t, and then closes it again. And all of this is in her proper time, and we assume that t is much larger than t1. And Alice can describe her particle in the beginning in terms of this wave function, where U stands for the upper branch and L for the lower branch of the superposition here. And without any external influence and without decoherence, so she's completely alone in the universe here, she can describe her particle in terms of this density matrix, where on the diagonals you would have the populations, so the classical probabilities to measure the particle in one of the two branches, and on the off diagonals, the coherences give you a measure of the interference probabilities. And without anything else, and also assuming that this opening and closing of her superposition happens adiabatically, so that she does not create any kind of variation during this process, she can describe also in the end, before she closes it, still her particle with this density matrix, and there's no decoherence, no influence from the surroundings. Now let's put the black hole into our model system here, and what changes then? And there are kind of two classes of work that discuss how this black hole influences the coherence of Alice's particle. One class is take the global point of view, where they consider the radiation which is sent out due to the presence of the black hole from Alice's superposition through the horizon, and therefore the information, roughly speaking, which is lost behind the horizon, which causes decoherence. And the other one is the local point of view, where the idea is that Alice should actually be able to determine what happens only with quantities available in her lab. So without measuring, in that sense, taking into account the radiation going through the black hole. And indeed, it was shown in these works that the vacuum of the electric or linear gravitational field in Alice's lab knows about the presence of the black hole. So one can also investigate the vacuum fluctuations in her lab to obtain the same effect, so the same decoherence effect. And the idea, I will follow the local approach here, is that the density matrix of Alice's particle can be derived, and in this work they indeed follow this influence functional approach to come up with this decoherence, which I mentioned in the beginning, can be derived to look like this. So it acts as some damping on the off-diagonal elements, and therefore she's not able, maybe this relates to your question at the beginning, she's not able to write it as a nice product state like this anymore than after a certain time. And they derived that this decoherence functional in the electromagnetic case looks like this. So it depends on the charge of Alice's particle, it depends on her superposition, how large the superposition is, the spatial superposition, and on the electromagnetic field, E, quantized on the Schwarzschild background, and then evaluated under the anti-commutator and the two-point correlation function with respect to the vacuum in her field, which in this case would be, for instance, Andrew vacuum or Hartle-Hawking vacuum, which yield to the same results in this application. And then what they find as a key result is that the presence of this horizon causes a constant decoherence, which goes linearly in capital T, the time the superposition is left open. And therefore, the mere presence of this horizon decoheres Alice's system. And this resolves, in this setting, the apparent paradoxon, if Bob can communicate with Alice outside the black hole. The answer is no, because his behavior, whether he measures or not, induces decoherence on Alice's system, but Alice's system decoheres nevertheless just due to the presence of this horizon. So she cannot retrieve any information from Bob. This is a very good question, something which we also thought about maybe discussing in a future project, if the decoherence changes or not. then. So if there's decoherence at all, because you would be on this trajectory or on this geodesic, or if there's no decoherence, or so this is something I'm very curious to know too. Okay, the crucial assumption in this, which I would call being a classical horizon geometry, was that all frequencies can enter the horizon, so can go into the black hole. And the question which we raised, so Alessandro Pesci and me, so my collaborator with whom I did the project then in Bologna, was what actually changes if the horizon geometry is quantum. And what do we mean by quantum? The motivation is that the space-time itself might be quantum, that is, that there might exist some minimal length. And these are all assumptions which may or may not be fulfilled, of course, but we worked here with these hypothetical assumptions that there is some minimal length in space-time, and then this would translate to the black hole to some effective quantization of the area, meaning there's a minimal quantum of area for the black hole or some area gap. And there are different proposals of the size of this area gap in the literature coming from different formulations of quantum gravity, but most of them hint to some area gap being of the order of the Planck length squared. And then the consequence of this is that the radiation coming to the black hole needs some minimal frequency, some minimal energy to interact with the black hole. You can maybe think of it, I don't know, it's an analogy that helps me, similar to an atom. If you have some atom and shoot radiation on this atom, if the radiation's frequency is too low, the atom cannot be excited to the next higher level, so radiation will not interact with the atom. And for the black hole, it would behave similar in this effective implementation. That if the radiation is too low to get over the area gap, then the black hole is not excited to the next higher quantum level, so the radiation could not interact with the black hole. And then we implemented this into this Gedanken experiment, and first of all, the main calculation here for this decoherence functional was carried out in the works I showed, always with the approximation that the main contribution comes from the very low frequency radiation. So I did some specific approximation to reduce the complexity of this integral, which is quite technical and not feasible as far as I'm aware of in general, because of this Schwarzschild quantization on Schwarzschild background in the form of the vacuum. But luckily, in this work here, they showed that one can describe the same effect by considering Alice being on an accelerated Rindler trajectory, with Rindler acceleration A, and her having a dipole instead of the superposition, and she opens and closes this dipole in the same temporal procedure. And then one can write down the decoherence. The formula looks similar, but the details are much simpler, because now the electromagnetic field is quantized on Minkowski background, and the Rindler trajectory only enters here in the x, so this is this accelerated trajectory, and the vacuum for the two-point correlation function is the Minkowski vacuum. And this simplifies the calculations a lot then, and the minimal area A0 translates then into a minimal frequency, which depends on the Rindler acceleration and on the minimal area. And below this frequency cutoff, the radiation cannot interact with the black hole in this implementation. This means the radiation does not contribute to the decoherence function. And then, evaluating this decoherence function, it turns out that the behavior indeed changes quite drastically, meaning that in the beginning there is some regime of quadratic increase in t, the same as it's in the other models, but usually t is assumed to be much larger, so that this regime does not contribute or does not show up. And then without any frequency cutoff, this means for a classical horizon geometry, we then get into this regime where the decoherence increases linearly with time. However, with an underlying quantum geometry with some frequency cutoff, turns out that we at some point run into a new regime 3 where the decoherence saturates. And if this frequency cutoff is sufficiently large, of the order of the Planck, the corresponding A0 would be of the order of the Planck length squared, then we even omit the regime of the linear increase and directly run into the saturation. And the remaining question from this now is, okay, how large is the saturation value? If it's of the order of 1, then Alice's system will anyhow decohere completely, so it doesn't play a role. But when we do this, and for this we went into the near horizon limit, thinking of that the decoherence should be the largest the closer we are to the black hole, because the stronger this gravitational influence should be, then it turns out that we obtain this formula here. And to give you an idea of this formula, the order of magnitude of the saturation value is the same order of magnitude of the radiation from Alice when she opens and closes her superposition, the radiation going to infinity, which was assumed from the beginning by the setting to be negligibly small. Now the decoherence coming from this horizon with quantum geometry, if the minimal area is of the order of the Planck length squared, is the same order of magnitude, so therefore also negligibly small. This means that if there is the horizon with this quantum geometry, then Alice's superposition is not decohered if this minimal area is sufficiently small, sufficiently large, here in the sense of the Planck length squared. And to conclude, this brings me back to the original question: how does this work with communication from Bob to Alice? We said for classical horizon geometries, no matter what Bob does, Alice's superposition anyhow decoheres due to the presence of a black hole. What happens now in the quantum case, so if we have horizons with quantum geometries, well, then the case is that the information on the superposition of Alice does not really get into the black hole, because the low frequency radiation is filtered out and cannot reach Bob in that sense. So Bob will not be able to entangle his particle sufficiently much with Alice's particle. And this means when he measures his particle in the end, then he will not get a really decisive, he will not get a really good result, and his measurement and the degree of entanglement, if there is any at all, is so bad that Alice's experiment here is almost not influenced by this one. So she will also not be able to retrieve any information from Bob. So this is the way then how to, again, restore the non-possibility of sending information to the outside of the horizon. Yes, sure.
So the limit was when the minimal length was of the order of the square of Planck.
Yes.
And then I didn't understand. So can I see
Sure.
this as a, because I want not to have any communication, then I need to have this minimal surface of the order of square of the Planck
Okay.
line. Can I argue like that?
So the other way around.
The other way around? Or the other way around?
Or, yeah, I would. Okay.
Your opinion, yeah?
Okay, sure. Yeah, I would say so. That then you can also do it this way around. That this kind of prevents the communication from Bob to Alice. That if not sufficiently much information can reach him to entangle his particle with Alice's particle, and therefore there has to be somehow this shielding. And one way to do this shielding is to implement or to put.
The surface will be, the minimal surface will be less than that, then there will be communication.
Yes. Then there will be so, and if the minimal surface is 0, then we would be in the classical case with this. There will not be in both directions communication, but the information can get at least to Bob, so he can entangle his particle. But the smaller the minimal area gets, yes, but the more decoherence comes again just from the presence of the black hole. So it's kind of this interplay. So if with the two extreme cases that A0 is very large, then there is no information going to Bob at all, so no chance to entangle. And the other limiting case, A0 being 0, then there is all information coming to Bob, but also complete decoherence coming from the presence of the horizon. And then the other things are somewhere in between. I would say that the decoherence from the horizon is less, so it takes longer to decohere Alice superposition, but Bob also has to wait longer to entangle his particle sufficiently much with Alice superposition. Yes?
Why would this argument not also work in, like, for instance, between us, right? We have the space-time microscopic that has minimal area spectrum. Same. Or we can think of between us there's someone else, correct?
I actually had the same doubt about this, but as far as I understood it, then it's a bit counterintuitive. At least for me, it was because the decoherence coming from the very low frequencies, which are filtered by the horizon. But if we have some minimal length between us, then this means or minimal area. Then okay, but or so. Okay, I think that's okay. I was going. If there's some minimal length, then this would filter out the very high frequencies. So in that sense, would not have. Or if there's some minimal length between us, so this would cut very small wavelength, which would be very large frequencies, which are then not able to, which we're not able to transmit. But the decoherence is caused by the very low frequencies. So this would not be a problem if there were some minimal length. So therefore, if there is some minimal length in the space-time, this decoherence and this sending of information would still be possible. But this black hole area is what changes the game then, because this is like a filter for the low frequencies. The minimal length would filter the high frequencies, and this black hole area, then the low frequencies to enter the black hole. But yeah, if we put something with minimal area between us, then I think it depends on what the thing between us is. If it's some kind of horizon like here, then which would really, like here, which would really filter the information, or if it's some kind of maybe wall or something, because then I would expect that the very low frequency radiation perceives this, so can just go through the wall, pass through the wall without interacting with it. So then I would expect that we can still communicate perfectly if there is some object, but then I would say the main point maybe in this effective implementation is that the horizon and the black hole does not interact with this low frequency radiation. However, one understands it so that the radiation just goes through the black hole, ignoring it, or if it's reflected, but that it does not interact with the black hole. And if you put some wall with this minimal kind of area between us, then also radiation would not interact. This means it just goes through. So then we would still be able to communicate almost perfectly, I would say. That's
Because like one particle, the whole soft hair is exactly this frequency of black hole, then it shelter.
this is a it's a good question, something which I'm not sure of. So I would say either like a mirror, but then this would again be some kind of interaction with the black hole, or it just goes through without seeing the black hole, which is so I would rather understand it as the radiation just goes through, because the wavelength is super long, so and that's the black hole is just one dip in this entire wave, that the wave just passes through and does not really see the black hole. Because if it were reflected, then there would again be some interactions or some absorption or whatever, which does exactly not happen in this implementation, at least. Okay. Yes.
In the second scenario, you said the problem to communicate through the horizon would be that you cannot entangle.
Mhm.
Wouldn't the solution be that Bob is first outside the black hole,
Ah,
entangle, and then he comes
into black. That's a very good question. I haven't thought about it. I'm not, I'm not sure how the time scales would work if the time. So if depending on which times all of this was formulated in terms of Alice time, proper time. So I'm not sure if this might prevent some the sending of information outside the black hole, depending on how Alice and Bob see the situation when they cross the horizon or not, and like this. Okay. No chance. It's a good question. How do I see what happens then? Because then, from Alice's perspective, if she's kept stationary in the metric, like then Bob would be accelerated. Maybe this already also destroys then the information, like this. Something. Oh yeah. Oh yeah, something like this. Forever. Thank you. Very interesting. Okay, but yeah, with this, let me conclude and come to the summary. So we discussed gravitational-induced decoherence. So decoherence coming from gravity in different models and different applications. The first one was this field theoretical setup where we had the Minkowski spacetime and our scalar field, whose dynamics we were interested in. And there the main points were the classical reference frame, so with this relational formalism, constructing suitable observables and physical time and length parameters which are with respect to these observables. And then we used the projection operator techniques to come up with a master equation. In the second part, we then went into the one particle projection. So consider one single scalar particle going through this environment of gravitational waves. And the main steps here were this quantum field theoretical renormalisation to remove the divergences, then the Markov and rotating wave approximation, and in the end, the application to ultra-relativistic scalar particles to end up with this rather short solution. And then we used this in the application to neutrino oscillations in this quantum mechanical toy model, investigate how decoherence actually affects these neutrino oscillations, and were able, at least in this toy model, to resolve the phenomenological parameters. And this match was only possible in vacuum, precisely. And in matter, these would deviate these two models. And in the end, we discussed decoherence induced by horizons, where we saw in the classical case, just the mere presence of the horizon completely decoheres Alice superposition, whereas in the case of a quantum geometry of the horizon, Alice superposition remains stable if the minimal area is sufficiently large, and the order of the Planck length squared is sufficiently large in that sense already. With that, let me thank you, and yeah, I'm happy to take any questions which are left.
Okay, thank you for the very nice talk. Okay, the microphone doesn't work. Yeah, I want to ask, so it seems the second part has a potential that, so you have this scalar field interact with linearized gravitational field. Did you think of, so one could think about, for instance, what kind of quantum signature of gravitational field this probe picked up? If you compare quantum linearized gravitational field versus this coupled to like classical linearized.
Like the classical linear.
Yeah.
This is a very good question. Actually, there are some works that consider, but there are also similar decoherence effects, maybe not in exactly the same settings, but they concluded that at least in this full field theoretical setup, instead of using this thermal state for this linearized gravitational wave background, when after quantization, one can equally use a specific classical distribution of gravitational waves with a specific Gaussian state, and then at least in the lowest order of the master equation, the one I displayed here, one can apparently restore the same effect there. But when one goes to higher orders, then I would say then when one goes to higher orders, is deviate. But in the lowest, in the dominant order, it seems that in specific cases, one can really match. And if you measure this effect, on the other hand, then if the conditions are in the specific setting, then you would a priori not be able to say if it's a quantum gravity effect or a classical gravity effect. You would have to dig deeper and go to higher orders then.
You mean at the leading order, classical and quantum linearized gravity would match?
Yeah.
At the leading order.
Yes. So there were some works on this where, indeed, by considering a suitably classical distribution then of this, so a stochastic gravitational waves background in some Gaussian state matched to this thermal state, because the reason for this, I have to go a bit back. Maybe let me stay here. I mean, it's a different factor, but the decoherence formula, in general, the reason for this is that what enters in the coefficients and in this decoherence coefficient is mainly the two-point correlation function of the environment. And if you have here the quantum state, so it's not in this setting, but the same arises in this other setting, then we would have the linearized gravitational waves in the Minkowski vacuum. And then what enters is only this two-point correlation function, so this expectation value. And then you can try to restore and get the same expectation value, the same outcome, if you use a classical distribution instead. And up to a certain degree, this is possible. Indeed so.
And I also want to ask, so do you see any effect coming from, for instance, the uncertainty relation between A and E from your probe? Do you pick up some signal from that?
That's a good question. I haven't thought about it yet.
Okay, because I feel from your formulation, you probably can check it
Okay.
immediately.
Yeah, I think maybe we can discuss later. Also, be cool to look into it. Thank you.
Thank you for the talk. Really interesting research direction, lots of results. I wanted to ask you maybe a very broad question. How is this setup that you have differs from linearized quantum gravity as a spin-2 field? You know, as you learn in textbooks, sort of thing. Like both in terms of like predictions, but also like maybe like more on a conceptual level.
I would say not at all, here at least, because this linearized formulation we used and then quantized it in the Fock quantization exactly leads to these spin-2 particles, which would be the gravitons here. The only difference maybe conceptually is that we use these Ashtika variables instead of the geometry dynamics, but they can be linked. So of course one would expect if one gets out this additional Gauss constraint, so solves this, that then they of course should physically yield the same. It's just another set of variables to describe the theory, but they are closely linked, and therefore also after quantization, this delta A and delta E can again be related directly to this spin-2 graviton formulation. And maybe a little hint. Okay, I have to go.
And sorry, before you go. And about the but so then the clock, this whole story of dressing with the clocks, like, do this just reduce to like Minkowski coordinates somehow, like the lab, what people call lab coordinates, or?
I would say it depends on how you pick these clocks and what the physical meaning is, but you could pick them very close to the standard gauge fixing. So some of the standard gauge fixings made in the spin-2 theories to end up with, again, the same degrees of freedoms, and then you can really match it and map it. So somehow some motivation for choosing specific clocks here. And some of them we try to match with this, because then we can directly have the same expression as in some of the other works where they use the gauge fixing. But these clocks are, I would say, more general because you can also switch them and pick different clocks and then compare between different gauge fixings a bit. So the final result depends, in that sense, intrinsically always still on your clock. And you can switch the clock also and then see how the final result changes.
Cool, thanks.
Thank you.
Thanks. No, mine is a maybe simple question, but I missed a little bit the link between your initial theoretical introduction and, for example, the model that you used for the phenomenological description of the neutrinos oscillation. Because in that model you used that Hamiltonian with that interaction term with the GI, QI, right? And I didn't understand, given that you used that Hamiltonian, what was the point of the initial relativization?
Of the initial?
Like all the initial relativization that you used. You used the relativization observables, then you defined clocks. And I didn't quite understood the relation between that first procedure and the Hamiltonian that you got in the final toy model. Like, my main question probably would be, what was the point of the initial part in relation to the final model, and then so in a way not the predictions, but the relation with the phenomenological observable gamma.
Thanks a lot. I would say the connection is the way how we understand x and t coordinates, so space and time then, as in this neutrino model in that sense. Of course, it's not completely one-to-one related, because it was a quantum mechanical toy model, which we started from this quantum Hamiltonian without any gauge degrees of freedoms in there, and also with gravity being mimicked by this oscillators, which also have no gauge degree of freedom. So in that sense, it was not required to do some similar formulation as relational observables, but one could imagine doing some quantum mechanical toy model which has some gauge degree of freedom. Then one could also do this there. So in that sense, there was no gauge degree of freedom to deal with, so we did not need to do all of this. But conceptually, I would say the link is between what space and time mean, these coordinates x and t, which are the taus of the clocks. And in this full field theoretical derivation, we needed to do this and to put this physical value to these x and t coordinates. And this I would say you can think of some concept what later X and T actually mean, but as this was not a general relativistic model, so based on GR, this problem or this point does not arise in general. So
Okay, and then why that toy model was, like why that interaction was the right one? Describing the, but maybe you already said this, but I missed it.
No, I'm not sure if it's the right one. So it's a toy model. So the hope is that it resembles some specific features sufficiently well enough, and the motivation to pick it like this comes also from this work here. And the idea is that if you write down this interaction term in this linearized gravitational field theory, which we had before, it would be something like T, so the energy momentum tensor for a scalar field, coupling to delta G, which is the metric, the perturbed metric, in the Hamiltonian formulation, the configuration variable of the gravitational degrees of freedom. And then this is mimicked here in the same sense by, replacing the energy momentum tensor by its 0,0 component, which would be just the energy of the system, of the scalar particle of the neutrino. And then for the environment, we also pick the configuration variable, which would be the position of the oscillators. So this is the motivation, but I know that people also in Erlangen, they were working also on different couplings and investigating how the outcome changes, and if you pick a different way to couple these two, because the form, how the final solution of the mass equation looks like, depends, of course, heavily on this and also in which base the decoherence happens.
So I guess we will conclude, but I would really like to see the case in which I start with Alice and Bob, just like in our paper, but they both freely falling. And then they entangled, if they want to. I mean, they wait until the long time that they could get entangled if Bob is releasing his particle, and then they are still distant enough. Bob is inside at some point, and then he can do whatever. And Alice is still outside. And now I don't see that there is a difference between this setup and the original setup in Minkowski space-time, which would be dangerous because Bob should not be able to send any information to Alice. Of course, I mean, this is now just a problem. I don't know, maybe if one look it more closely, one would see that this doesn't work. I mean, then the problem is like in our paper. And then Bob still has the ability to...
But why, like, is it released or not released, this you mean? Or
Yeah.
But there you just take, no. There's no gravitational field that pulls anything.
No, but they are already entangled before, and then he is inside.
But then she would decohere no matter what.
Why?
Because he cannot send the coherence back to her.
But no, sorry, no, it's not decoherent. It's not already entangled. Sorry. He's with the particle in the trap going inside, and then deciding.
The trap will pull nothing.
No, but the trap is freely falling with, I mean, the whole laboratory of Bob is freely falling, and the whole laboratory of Alice is freely falling. Bob has, within the laboratory, still a freedom to release the particle or not to release the particle.
Say he releases, then the particle will not get entangled.
Right. Well, that's the question.
Keep floating there. There's no force. There's nothing. No? He's free falling. He doesn't feel anything.
Yeah, doesn't feel even the gravitational field of Alice. Yeah. That's the answer, yeah? True. Thanks, yeah. So they will not be able to entangle.
But if Bob is free falling in the superposition of this device, then he's going to get entangled.
Quantum free falling frame.
Yeah, exactly.
It's a quantum free falling flame, yeah.
Yes.
But he wouldn't be able to decohere in a sense. He wouldn't be able to dance, but
Yeah.
Alice should decohere.
I don't think it's free falling.
It's free falling, yeah. It's free falling in both of the positions of both branches, yeah. Good. Thank you very much.
Thank you a lot. Thanks. maybe I will be here until Thursday evening. So if someone wants to discuss, I got